In this video, we're going to talk about increasing, decreasing, and monotonic sequences. So here's the definition. Let's say that we have a sequence a sub n of real numbers. Then we say that it's increasing if a1 is less than or equal to a2, and a2 is less than or equal to a3 is less than or equal to a4, etc. We say that it's decreasing if a1 is greater than or equal to a2 is greater than or equal to a3 is greater than or equal to a4, etc. And we say that an is monotonic or monotone, depending on the book, if it is either increasing or decreasing. Now keep in mind that the numbers in the sequence, if the sequence is increasing, the numbers either stay the same or they increase, they actually get bigger at every step. So let's look at some examples. So if you have the sequence 1, 2, 3, 4, etc., that is certainly increasing. What if you had 2, 2, 2, 2, ... From the definition, what is this? This is increasing and decreasing. Right? From the definition, you just need less than or equal to. And for decreasing, you need greater than or equal to. So if all the terms of the sequence are the same, then the sequence is increasing and decreasing. So notice that this may be different than what you might be used to when you're thinking of increasing or decreasing, but from the definition, right, if we use the definition, we see that it literally is an increasing sequence and a decreasing sequence. Okay. What about something like 0, 1, 0, 1, 0, 1, etc.? Okay, you could pause the video and take a few seconds. Well, this sequence is neither increasing nor decreasing. Right? It doesn't satisfy either the conditions of the definition. In particular, this is not increasing and decreasing, right? So don't think, well, it increased from 0 to 1, and then it decreased from 1 to 0, and then increased and decreased, so it must be increasing and decreasing. That's not true. If you read the definition, okay, the sequence doesn't satisfy either of these requirements. So these two sequences are monotonic. That one is not monotonic. All right. Now we come to this theorem. It's called the Monotonic Convergence Theorem. This is an important theorem because we'll end up using it in proving other theorems. So the theorem says that every bounded monotonic sequence of real numbers I'll just put this in parentheses because we know we're working with real numbers. Every bounded monotonic sequence is convergent. Now, before we get to the proof, let's just make some comments. First of all, we know that every convergent sequence is bounded. Okay, so think back about how we might prove that statement. And suppose that we remove this monotonic part. So suppose that we just deleted the word monotonic and said every bounded sequence is convergent. Well, that's certainly not true, right? If you take the sequence 1, -1, 1, -1, going on and on and on, that is a bounded sequence, but it's not convergent. So the monotonic part is an essential hypothesis in the theorem. All right, let's see the proof. So if you have a monotonic sequence that's bounded, the sequence is either increasing or decreasing, right? So let this sequence AN be a bounded monotonic sequence. So we want to show it's convergent. Now suppose that this sequence is increasing. Okay, you do the part where it's decreasing. It's pretty much exactly the same. Okay, so I'll just do the part where it's increasing, and then you figure out the part where it's decreasing. So we have an increasing bounded sequence. Well, since the sequence is bounded, what can we say about this is a bounded set of real numbers? This is a bounded non-empty set of real numbers. So what does it have? It has a supremum, right? Since the sequence is bounded, the set consisting of A1, A2, etc. has a supremum, which we'll call A star. And what we'll show is that the sequence AN converges to the supremum. Okay. Now, to do that, we should let epsilon be greater than 0. So we want to show that there exists some positive integer n such that for all little n greater than n, the difference between a sub n and a star is less than epsilon, right? That's what it means for the sequence to converge to a star. Well, so let's draw a little picture. So you have some sequence that's increasing and it's bounded. And the idea is that we want to show that the sequence converges to the supremum. And we have some epsilon neighborhood. Okay. So once we know that this interval contains a point of our sequence, then we can see that it will contain all the points after that because the sequence is increasing. So how do we know that there is even a point in this interval? How do we know there's a point in the sequence that's inside this interval? Well, this follows from the fact that A star is a least upper bound, right? So let's look at the point A star. So let's look at this number. That's A star minus epsilon. Oops. A star minus epsilon, right? And this one is A star plus epsilon. Well, we know that A star is the least upper bound of the set A1, A2, etc., then we know that A star minus epsilon is not an upper bound of the set. Let's call this set S, just so I don't have to keep writing it. Right? Because if it were an upper bound, then that would be a smaller upper bound than A star, but A star was the least upper bound. So since A star minus epsilon is not an upper bound of S, that means that there exists an element of S that's greater than A star minus epsilon. And the elements of S are the terms of the sequence. So there exists some n such that A sub n is greater than A star minus epsilon. Now, since A star is an upper bound, of S, we actually have that an is also less than A star, right? So we know that this interval contains some A sub n, so there's going to be like some A sub capital N here. Okay, in the interval, in this interval. And now we see what's going to happen. Since this sequence is increasing, all the terms past the A sub capital N will also be in this interval, and then that will prove the theorem. So since, let little n be greater than capital N, since the sequence is increasing, we have A star minus epsilon is less than A capital N, less than or equal to A sub little n is less than or equal to A star. Actually, we really have less than or equal to A star, right? Okay. But that means that an is in the open interval of radius epsilon centered at A star. And that concludes the proof. Because little n was just any integer greater than capital N. Okay, so that's the proof of the monotonic convergence theorem. And the key fact we needed was the least upper bound property, right? We actually showed that whenever you have a bounded monotonic sequence, it converges to the least upper bound of that sequence. So it's not just convergent, we actually know what it converges to. It converges to the least upper bound. Actually, like I said before, we only prove this in the case when the sequence is increasing, and think about what you can do to an increasing sequence to get a decreasing sequence. And what you can do, actually, since that second part of the proof is to start with a decreasing sequence, you really want to think about what you can do to the decreasing sequence to get an increasing sequence. And these are real numbers, right? So think about that and see if you can finish the proof. Okay. So what we did in this video is we defined increasing, decreasing, and monotonic sequences. We looked at some examples, and then we proved part of the monotonic convergence theorem. And this theorem, like I said, will be used in proofs of other theorems that we'll be discussing. Thanks.